A lecture on gravity, Part A, bringing it all together. First topic, falling around. Newton's explanation for orbital motion. Here we see a picture of the Earth. The Earth's curvature is such that it drops or curves 5 meters from a horizontal every 8,000 meters along the surface. What this means is, if you were to travel in a straight line for 8,000 meters or 8 kilometers, such as you built a very long 8,000 meter long table or rail, after 8,000 meters, this horizontal line or horizontal table or track would be 5 meters above the curved Earth. For example, looking from a beach, you can only see a ship that is at least 5 meters tall if it is 8 kilometers away. So we see ships rising above the horizon, mast first, and then the rest of the ship comes up later. If the ship is 8,000 meters away, the ship has to be taller than 5 meters. The top of the ship has to be taller than 5 meters from the bottom for it to be seen. Now, if a rifle can fire a bullet to travel at least 8 kilometers horizontally in 1 second, then it would follow the curvature of the Earth as it falls. So if we take a high-powered rifle, aim it parallel or horizontal to the ground, with a speed of at least 8,000 meters per second, then as it travels horizontally 8,000 meters at a constant speed of 8 kilometers per second, neglecting air resistance, then gravity would cause it to fall 5 meters after 1 second. Recall and check this calculation from your kinematic equations that all things fall 5 meters after 1 second. So if the ball that travels 8 kilometers after 1 second falls 5 meters, it's still right above the Earth. Shooting any faster than that, it'll be above the Earth. Any slower than that, and it'll hit the Earth. Thus, if it has this horizontal speed of 8 kilometers per second, it will constantly be able to fall 5 meters as it tries to fall towards the Earth, falling 5 meters for each second as it travels 8 kilometers, constantly following or falling around the Earth. Let's look at some animations that show this idea. If the launch speed is less than 8 kilometers per second in the horizontal direction, then here we have a cannon shooting a cannonball, and it falls eventually to the Earth. Newton, in his great work, The Principia, drew a picture, an illustration of something similar to this, a giant cannon atop of a mountain, where the cannonball is shot from the top of the mountain horizontal to the surface of the Earth, neglecting air resistance. Eventually it follows a parabolic motion that impacts the Earth. But if this giant cannon is shooting the cannonball faster and faster, the cannonball travels farther and farther, always falling towards the Earth 5 meters after the first second. The launch speed is just a bit less than 8 kilometers per second, but faster than previously. It'll travel farther along. If the launch speed equals 8 kilometers per second, it always falls 5 meters after every second, which matches the curvature of the Earth. So it goes all the ways around the Earth. And launch speed greater than 8 kilometers per second, the orbit would be an ellipse, a stretched out circle. This is Newton's explanation for how objects can orbit the Earth. This is essentially how we make objects such as satellites orbit the Earth. We shoot them with speeds greater than 8 kilometers per second. With air resistance, we'd have to shoot an object significantly faster than 8 kilometers per second if we wanted to travel around the Earth near the surface, ignoring mountains and trees. Newton also used this explanation to explain why the moon is in orbit around the Earth. Essentially, it's being thrown at a great speed to fall, just as any object falls around the Earth, but at a great enough speed so it always falls to follow the curvature, always falls or falls around the Earth. There's a legend that Newton was sitting outside on his land under an apple tree, and he watched an apple fall to the ground, or it hit his head. And he thought, the same reason that an apple or any object falls to the ground, and if I take an apple and throw it, it will fall to the ground, or any object, as you know from previous material with projectile motion. What if the moon obeys the same exact principles, the same exact patterns or laws? The moon is simply being thrown like the apple, but also subject to fall towards the earth or attracted to the earth. So why does the moon not fall to the earth the same way the apple falls to the earth? Perhaps the moon has enough speed to follow a great projectile path, so it's always falling towards the earth, but falling around the curved earth. If the apple is thrown with 8 kilometers per second at 5 meters above the earth, then the apple will be able to go around the earth if we can ignore air resistance and not hit any objects as it travels around. So maybe the moon, much farther away, is essentially being thrown to fall around the earth, but perhaps the attraction of the earth to the apple is similar to the attraction of the earth to the moon. The earth is pulling on the apple the same way it pulls on the moon, but much less because the moon is so much farther away. So therefore it doesn't fall 5 meters for each second, but it falls a little bit less than that, and so the moon travels a much greater path as it falls around the earth. This was Newton's idea. Essentially, what if you shot the moon from a giant cannon atop a gigantic mountain around the earth? Perhaps it would simply fall or orbit around the earth. That's what's being shown in these illustrations. In short, the moon falls around the earth the same way as a projectile would fall around the earth given the right speed to always fall around the curved earth. Newton calculated what must be the gravitational attraction, or the fall, the distance that the earth is from the moon. He knew the speed you'd have to throw the apple. By knowing how quickly an apple falls to the earth, at 5 meters for the first second, how quickly would the moon have to fall to the earth for it to curve in the great path that it takes for the moon to go around the earth? So he knows the time it takes for the moon to go around the earth, 1 month, and if the distance from the earth to the moon is known, he can figure out the force of attraction, the gravitational attraction, the pull that makes the moon essentially fall around the earth. The music of the spheres, the description of orbital motion of the moon and planets and stars. In ancient times, particularly ancient Greece, it was believed that all objects in the heavens revolve around the earth. Not that the earth rotates about itself once a day, but that the earth is stationary and the planets and the sun all rotate about the earth. A geostationary, an earth-stationary, earth-centered picture. Geocentric idea. Venus and Mars, the rest of the planets, the moon and the sun all go around the earth. They go around in these great spheres, or great shells, that can be described with mathematical ratios or the music of the spheres. This was the belief up until Copernicus and Kepler and Newton. But one thing was not quite understood. The motion of Venus and Jupiter and Saturn wasn't quite moving around the Earth in perfect circles. What we see here is the motion of Mars, as we saw in the previous animation, the motion of Jupiter and Saturn from Astronomy Picture of the Day. If you follow the motion of the planets, they move from night to night across the night sky. So looking here, we see on October 7th, and then October 13th, and then October 19th, the position of Mars each and every one of those nights. We see Mars has made a loop. It goes in one direction, and then it loops backwards, and then returns to follow that same direction. This is known as retrograde, the looping backwards motion. Why Mars has a great retrograde or loop in its motion, going backwards motion for part of its cycle, and why Jupiter and Saturn have the same retrograde motion but at a smaller scale, was never understood. The ancients, in their geocentric, earth-centered system, believed that the planets go around in great spheres, but the planets were going around in great spheres on smaller circular orbits, or sometimes circular orbits upon the great spheres. Sort of like at the amusement park rides, the teacups, where the teacups spin around themselves, or rotate around themselves, and then the teacups are on rotating arms that rotate around, and you have very complicated motions built on circles upon circles upon circles. The ancients got more and more precise, plotting the position of the planets through the sky, saying the planets are moving around epicycles or circles upon circles to describe the retrograde motion. In essence, no one quite understood why the planets had this retrograde motion. Johannes Kepler, studying the work of Tycho Brahe and Nicholas Copernicus, followed the idea that perhaps the Earth wasn't the center of the universe, that the Earth was just another world, another planet, a planet that went around the sun as all the planets did. If the planet went around the sun, not in a perfect circle, but in an ellipse, then the motion of all the planets, including the retrograde motion of the planets observed, could be explained. Johannes Kepler was a model maker. He believed that perhaps there is geometric patterns that can describe the heavens. He asked, how are things happening? How is it that planets are moving around the sky? He was a mathematician, a physicist, a scientist, and a philosopher, and also was paid to be an astrologer and a mystic, trying to figure out the precise positions of the planets in the sky for royal courts who wanted to know whether it was a good day or not to declare war or to make a treaty by the positions of the planets in the sky. In essence, he tried to find patterns or math behind the positions of the planets, or try to find the music in the sky. He tried to explain the distances of the 5 known planets by spheres resting on the five mathematical bodies, the five perfect solids. This was all pre-scientific work. Eventually, Kepler realized that despite all his wishes for his perfect models to describe the Earth going around the sun in perfect circles along with the planets, he abandoned this perfection, this music of the spheres, and said perhaps the planets, including the Earth, go around in imperfect circles, in stretched circles or ellipses, that they go around in elliptical orbits. And this is Kepler's first law. Kepler's first law is the orbits of the planets are ellipses, with the sun at one focus. What's an ellipse? An ellipse is a stretched circle with a major axis and a minor axis. If you take 2 thumbtacks, tie a string between them, and put a pencil along the string, you would trace out an ellipse. The 2 tacks are called foci. The 2 foci are each is a focus of an ellipse. The distance between the tacks, so the distance between the foci, is known as the eccentricity. When the eccentricity, or lowercase e, is equal to 0, the 2 tacks, or the 2 foci, are on top of each other, and you have a perfect circle. When the tacks are separated, or the foci are separated, the circle is stretched or becomes eccentric, off-center. The more off-center the tacks are, the more eccentric or stretched or elongated is the circle, or increasing the eccentricity as you're going from a circle to the imperfect ellipse. The long axis of the ellipse is the major axis. The smallest axis of the ellipse is the minor axis. The semi-major axis is the half semi of a circle. We use the letter A as a common symbol to represent the semi-major axis. Perihelion is the closest approach a planet has to one of the foci. The sun sits at one focus. The other focus is simply an empty mathematical point. And the Earth and the other planets go around the sun, where the sun is at one focus. When the Earth or any planet makes its closest approach to the sun, it's a semi-major axis distance away, or distance A away. This is known as the perihelion. Helios, or helion, means sun. Perihelion is the closest distance to the sun. Like a periscope gets you closer towards an image, a perihelion gets you closest to the sun. Aphelion is the farthest from the sun. Kepler's second law is planets go around in their elliptical orbits, making equal areas in the elliptical orbits in equal times. Shown in this illustration is a planet traveling around in a year. The sweep of the planet over, let's say, 1 week sweeps out an area of the orbit. The planet On the opposite side of the orbit, half a year later, for 1 week, we'll sweep out an equal area in the orbit again. So when the planet is close, it sweeps out a fat triangular shape, as you see on the illustration. It sweeps up this fat triangular shape during one period of time, 1 week, or let's say 1 month, during the motion, Earth's motion during January, perhaps, as in the illustration. Then when it's farther from the sun, making the big long triangle, the long skinny triangle compared to the fat close triangle, the long skinny triangle, the Earth in July, a half a year later, is traveling slower. So over that same period, equal period of time, it travels slower, farther away to sweep out an equal area. So an imaginary line connecting the sun to any planet sweeps out equal areas of the ellipse in equal times. What this means is it moves faster when it's closer to the sun and moves proportionally slower the farther away it is from the sun. This is actually an example of conservation of angular momentum. The motion of the planet is the momentum. The distance that the planet is from the sun is the distance vector, the position vector r. Recall that momentum, angular momentum, is r cross p. So when the object is far away, the r is great, and the p, the momentum, is less. Kepler's third law, objects moving in smaller orbits have smaller periods or shorter periods of time to complete their orbits, or shorter years. A planet with a longer year is a larger orbit. The mathematical relationship, the square of a planet's orbital period, is proportional to the cube of its orbital semi-major axis. P stands for the period. A stands for the semi-major axis. So the square of the period, or the square of the planet's year, is equal to the cube of the distance, the greatest distance, the semi-major axis. The common distance used among planets is an astronomical unit. So the new unit, the average distance from the Earth to the Sun, is called an astronomical unit, or an AU. An astronomical unit is the distance from the Earth to the Sun. So for instance, if a planet is 3 times as far away from the Earth to the Sun, it's 3 AU. Astronomical unit AU is about 1.5 times 10 to the 11th meters. Of course, it's an incredible distance. So what if the period of a planet is 8 years? How large is the semi-major axis? Well, the period squared is equal to the semi-major axis cubed. So 8 years squared is 64 years. Therefore, 64 years is equal to the cube of the semi-major axis. What number will we have to cube times 3 times to get the same value of 8 squared, or 64? Well, the cube root of 64 is 4, because 4 times 4 times 4 is 64. 4 times 4 is 16, times 4 again is 64. Looking at the planets, the 8 major planets, if we cube the semi-major axis of Mercury and square the period of Mercury, we see we get the same value of 0.006. If we cube the semi-major axis of Venus and the square of the period of Venus, we get 0.37 for both values. 1 for both for the Earth, such as Saturn, square the period, cube the distance, and the number is almost spot on. This shows us that the planets moving around the sun follow Kepler's third law. Continue now to part B for Newton's explanation in the next generation following Kepler, how Newton explained the empirical results that Kepler got from his data. What is the reason behind Kepler's laws?